Problem 212, page 40 of the book Strength of Materials by Pytel and Singer. The rigid bar ABC shown in the figure is hinged at A and supported by steel rod at B. Determine the largest load P that can be applied at C. If the stress in the steel rod is limited to 30 ksi, and the vertical movement of end C must not exceed 0.1 inch. I have drawn here two figures. One is the free body diagram of the rigid bar ABC, and another the final position of the rigid bar after the application of the load P. So we are given that the stress here in the steel is limited to 30 ksi, and the movement here y is limited to 0.1 inch. So there are two ways of solving this one. One would be consider the free body diagram here and then solve for n in terms of P by summation of moment at A. We'll be able to solve for n in terms of P, and then with the stress formula, this now in terms of P, this is given to be 30 ksi and we have the area, therefore we can solve for P from here. Then from this drawing, we solve for this elongation of the steel here by ratio and proportion. If we use y equals 0.1, then we can solve for delta S. With delta S already solved, we can use this formula. And again, n is already in terms of P. This is now solved, given, and this one is given. So we get another value for P using this formula. So we have two values for P, and from there, we are going to determine which is the maximum load that can be applied to this rigid bar at point C without exceeding these two conditions here. So that's one solution. Another solution would be to use Hooke's law, which is stress equals modulus of elasticity times strain, where strain is delta over L. Okay? So we have a relation between stress and the deformation. Okay? So let us solve for delta S first, this one. Delta S by ratio and proportion over 2 equals y over 5. Let's say we will use the limit for y, which is 0.1, and we'll have delta S equals 0.1 divided by 5 times 2 is 0.04 inch, or delta S is not to exceed 0.04 inch. Going back this relation, we have stress in the steel equals the modulus of elasticity, which is 29 times 10 to the 6 psi. Let's convert that to ksi so that it will match the given limit for the stress. So we will divide this by 1000. Multiply that by the elongation for steel divided by the original length, which is 4. Then let's convert this to inches so that our result for delta S will be in inches. So stress sub S equals 29 times 10 to the 6 divided by 1000 divided by 4 divided by 12 equals 604.17 times delta S. Okay, let us say, for example, the stress will reach the maximum of 30 psi. Using this relation, you have 30 equals 604.17 times delta S, and delta S equals 30 divided by 604.17 is 0.05 inch. And this is more than the limit of 0.04 inch. Okay? If we use the limit for a deformation, which is just 0.04 inch, how much should be the stress? That's 604.17 times the delta, which is this one, (604.17) times 0.04 equals 24.17 KSI. This is less than 30 KSI. Therefore, the stress is 24.17 KSI. And with this stress, our elongation for the steel, delta S, is 0.04 inch. And this by ratio proportion will give the movement at C to be 0.1 inch. Okay? So we will use this one. We go back to the free body diagram. We sum up moment at A, equate that to 0 for equilibrium. We will be able to solve for N in terms of P. So we have P times 5 minus N times 2 equals 0. N is 5 halves of P. Okay. Then from stress in the steel equals N over area of steel. We now use this for the stress, 24.17 equals N, which is 5 halves of P, over S, which is 0.5. We get P equals 24.17 times 0.5 times 2 divided by 5 equals 4.83 kips.